Good morning. I'm Fumin Jiang, currently a professor at Georgia Tech. I'll soon become a chair professor at the Hong Kong University of Science and Technology. I will also serve as the director for the Chiang Kai-shek Robotics Institute. In this talk, I will offer some insights on the great topic of marine robotics, which is an enabling technology for ocean applications. For this, I call the ocean applications the blue economy. I would like to motivate my talk with a past tragedy that occupied the center stage of public attention 12 years ago. On April 20th, 2010, an explosion on the Macondo oil drilling platform in the Gulf of Mexico suddenly occurred, taking the lives of 11 workers and injured 17. The disaster did not stop there. For nearly 3 months, more than 200 million gallons of crude oil leaked into the Gulf of Mexico. By the time of July 2010, as shown in the right figure, the leak oil has reached a vast coastal area around the Gulf of Mexico. Each black spot on the map indicates a place where severe oil pollution has been observed. It took 3 months to stop the oil leak and another 2 months to completely seal the well. This tragedy and a chain of disastrous events in recent years, like Katrina and Indian Ocean tsunami, reveal the tension between human society and the marine environment. It also shows the need to further understand ocean phenomena. After the explosion happened, several attempts were made to seal the leaking wellhead more than 1,000 meters below the water surface. No diver could reach the steps. Therefore, several remotely operated vehicles, or ROVs, were employed to perform the operation. The left figure showed one of the attempts where the ROVs were trying to install an oil collection cap over the well. The ROVs are connected to a supporting vessel through cables that are more than 2 kilometers long. The right figure showed one of the ROVs used in operation developed by Schilling. The ROV is a powerful robot as big as a pickup truck. It takes several operators to control its movements through the cable underwater. Without these kind of ROVs, the oil and gas industry cannot function in deep water. The key technologies for remotely operated vehicles include the vehicle platforms and the underwater manipulators. Here, I listed some of the major providers of the vehicles and the underwater manipulators. Each of the ROVs costs about 10 million US dollars. Until today, the global market for world-class ROVs has been dominated by European and US companies. After the wellhead was sealed, it takes more than a year to clean the oil contamination. My team at Georgia Tech has participated in the pollution monitoring effort in 2011. 1 year after the oil spill event, my team went to the Grand Isle State Park, where a tidal lagoon is connected to the ocean. Polluted ocean water flew in during high tides. When we arrived, there was still ongoing cleaning effort on the beach. In the right figure, we can see a cleaning vessel deploying oil dispersant on the barrier rocks to wash oil spills off the rocks. As we reach there, there are still personnel on the beach trying to pinpoint polluted sands and try to collect these sand so that they can be washed and put back. This video demonstrates an autonomous surface vehicle developed by our students in 2011. The vehicle hosted an optic-based oil spill sensor that were able to measure the level of oil concentrations on the water surface. The autonomous boat was able to track circular and straight line trajectories to survey the area. We performed the experiments during the summertime in 2011. The temperature was nearly 40 degrees Celsius, and there were many mosquitoes in the area of survey. This is why we need to develop marine robots to perform these survey tasks instead of having human beings to do it. Through autonomous survey, we get bathymetry map for the tidal lagoon. For the map, we can see that the maximum depth in the pond is about 1.65 meters. The southwest of the pond is deeper than the other parts. We can also see the bottom shape of the pond from the middle figure. We have observed a low level of oil concentration on the surface of the lagoon. The level is not immediate toxic, but it may have longer-term negative impact on the environment and the wildlife around the lagoon. So the oil spill event I mentioned reflects the tension between the human needs and the ocean environment. The human society have always been looking into the ocean environment to satisfy our needs. As the resources on land are depleting, we have seen increasing demand for ocean resources. For example, oil and drilling and minerals underwater and aqua farming, getting more fish raised in aqua farms, more transportation needs, and more energy harvesting needs. Marine robots have great potentials to provide services to address these needs. Robots can help divers to stay safe, to move like dolphins. Robots can explore the deepest ends of the seafloor. They can also inspect the fish farms to keep our food source secure. We have seen increasing needs for marine robots in port operations, wind and wave energy harvesting, and aquaculture. We will need marine robots to offer great services for humans to achieve self-fulfillment and a better life. To answer the great challenges in blue economy, marine robots have to deal with great difficulties that is associated with a highly unpredictable ocean environment. Here, I was always asked the question, why marine robotics is so difficult? So first, communication underwater is very difficult. Electromagnetic waves cannot penetrate seawater. Hence, underwater communication, sensing, and localization have to rely on acoustic signals. Comparing to electromagnetic signals, which operate in megahertz and gigahertz range, acoustic signals have very low frequency in the kilohertz range. Hence, the bandwidth of acoustic signals is quite narrow, and the bit rate of communication is very low. Therefore, communication and localization performance underwater is very low. Another severe constraint for ocean observation is limited power. Since the ocean is constantly moving with waves and currents, marine robots need to consume more energy than their counterparts on land to move around. However, obtaining power in the ocean is quite difficult too. Future developments in marine robotics have to answer these great challenges. Let us first see some of the effort to develop the next generation of remotely operated vehicles for underwater manipulation. This movie shows reconfigurable and transformable platforms to support a manipulative operation in different modes. The ROVs have two arms like humans that can perform dexterous operations, and multiple ROVs can coordinate with each other to perform complicated tasks. The middle movie show a bottom docking and dwelling systems. ROVs can switch between tethered and untethered modes depending on the mission needs. The vehicles can autonomously go charging when needed. Having the ROVs reside in the bottom can significantly reduce the overhead of deployment and recovery. The right movies showed research to reduce the workload of operators using modern human-robot interface technology. The operators can control the movement of the robot arms through a master-slave arm-hand movement. The vehicle can also use full virtual reality capability to reduce the workload of human operator to make operation in the undersea environment much easier. Other than underwater manipulation, we also need to more effectively collect information from the ocean. The ocean is vast and ever-changing. So far, only a small portion of the ocean has been explored by mankind. Ocean observation requires a lot of sensors. We need these sensors to be able to report data back to us. Hence, the sensors would need to be able to form networks to pass data from the ocean to us. Up to now, there are two types of sensor networks. One type is a static sensor network. In certain locations of the coastal ocean, long and thick backbone cables have been installed on the sea bottom. These backbone cables provide power and communication support for the network. Then junction boxes are installed along these backbone cables. Each junction box can host a set of sensor nodes that are connected to the box. The box provides power and communication support for the sensor nodes. Another type of sensor network is the mobile sensor network. Instead of being installed at a fixed location, the sensors are carried by moving platforms. Many of these platforms are robots that can fly in the sky or swim in the ocean. While moving through the air or the water, the sensors on board the moving platforms collect data from the ocean environment. The moving platforms provide both power and communication support for the sensors to collect data. We see that mobile sensor networks can be deployed at different locations according to different sensing need, but the operation time is limited by the amount of power available for each of the mobile platforms. One of the most popular marine robots for ocean sensing is the underwater gliders. As the movie shows, underwater gliders move in the ocean by changing its buoyancy. The joint force of gravity and buoyancy creates a sawtooth trajectory that consumes very little energy. Gliders can operate in the ocean 24 hours, 7 days uninterruptedly for months or even years. Hence, it is a perfect platform for ocean sensing and data collection. A glider can host a variety of ocean sensors to measure the physical properties of the seawater and the biological contents. Underwater gliders can also host acoustic communication devices so that they can communicate and transmit the sensor readings in real time back to us. Underwater gliders have become one of the most important ocean sensing platforms in recent years. Other than the underwater gliders, other types of long-duration ocean observation robots have been developed in recent years. For example, the wave glider is a surface boat that is able to harvest wave energy and solar energy. The sail drone is an autonomous sailboat that is able to use wind energy to move around and to collect data. These platforms can form a three-dimensional observation networks with underwater gliders. There are also new advancements in sensor development for these long-duration observation robots. For example, multimedia sensors are now available to take videos and sounds at the same time in the ocean. There is also a trend to use many ocean observation robots at the same time. For example, the US Navy has operated more than 50 underwater gliders at the same time about 2 or 3 years ago. How can we make these marine robots move and operate autonomously? A marine robot usually comes with an autopilot software that provides basic functionalities such as moving to specified GPS location called a waypoint to enable autonomous ocean sensing. This functionality is not enough. Another feedback control loop needs to be added. We call this loop a cyber cycle. The goal of the cyber cycle is to use all the information available to provide guidance for the marine robots. First, measurements from the available sensors in the network are collected. Then these measurements are used by ocean models through a procedure called data simulation. The measurements are used to generate future predictions of the ocean states by the ocean models. The ocean models are usually computed by high-performance computers. The model prediction is then used by autonomous planning algorithms to generate waypoints for the robot. Once a list of waypoints are received, the robot uses its autopilot to move about and to reach the waypoint. This process is run iteratively. Every time a new set of measurements are available, the cyber cycle will be triggered to generate a new set of waypoints for the marine robots to follow. This way, the robot can perform autonomous sensing in the ocean guided by the ocean models and the sensor information collected. This autonomy architecture also connects the edge computing performed on the marine robot and the cloud computing performed by computers running ocean models. When we have more collected data, we can apply AI and data-driven technologies to generate something called a generic environmental model to bridge the gap between edge computing and the cloud computing. Our goal is to reduce the number of human operators in an ocean environment through AI and data-driven methods. The autonomy for swarm of marine robots have seen measurable success in recent years. Since 2015, my team has been supporting underwater glider missions to observe coastal ocean in the southeast region of the United States. We have been providing autonomy service for the glider deployments. Here, I want to give one example. The right figure shows a 2018 mission in the North Atlantic Ocean, where nearly 30 underwater gliders from NOAA, NSF, and US Navy are deployed to observe 3 hurricanes at the same time. These robots form data collection networks that provide useful data to make more accurate hurricane predictions. Based on the data, the stakeholders and policymakers can decide whether an evacuation plan is needed in certain coastal area when hurricane comes. Given all these recent developments, our goal for the future is to send more marine robots to the sea, not humans. I would like to point out that the research community for marine robotics has been relatively small historically. Rapid recent growth has been observed worldwide. And also most existing marine robots are developed for oil and gas industry, Navy applications, and scientific explorations. There are very small number of marine robots for other applications, mostly in the fundamental research domain or early stages of industrial prototypes. Therefore, there are many opportunities for new business developments in marine robotics for blue economy. With that, I finish my talk today. Thank you for listening.